Welcome back. We're going to pick up where the last lecture left off. We were talking about operator splitting, and in particular, we had seen that the Peaceman-Ratchford operator, which is the composition of the two Cayley operators, has as a fixed point the solution to the generalized equations of the sum of two relations. So, and in particular, we had seen the specialization of that to the kind of problems that we care about that lend themselves to splitting. So we're always thinking about something like this: minimize f of x plus g of x. The generalized equation that this is, of course, equivalent to in the presence of convexity is 0 is an element of the subdifferential of x plus the subdifferential of g, and Douglas Ratchford is basically the simple idea of realizing that the fixed points of the composition of the Cayley operator of f and the Cayley operator of g solve this equation. We saw in the previous lecture that this composition is non-expansive, and therefore, in particular, iterating it will not guarantee convergence, but we do know that we can now form an averaged operator, and iterating that will guarantee convergence. And sorry, apologies, to make sure that of course it doesn't matter. The algorithm is not symmetric in f and g, but of course we can interchange these. But just to be consistent with my previous notation, let me write it in this way. And so the Douglas-Ratchford algorithm is based on the fact that, again, this composition is non-expansive, and therefore the operator 1/2 of identity plus this is firmly non-expansive. In particular, it's 1/2 averaged. And so iterating it is guaranteed to converge to a fixed point of the operator. And as we've discussed, the fixed point of an averaged operator is the fixed point is the same as a set of fixed points of the non-expansive operator. So this idea solves the problem and gives a solution to this set of generalized equations. And we saw that if we specialize it to the particular case where f and g are closed convex functions, again, as previous lectures explain, if a function f is convex, then its subdifferential is monotone. And if it is closed and convex, then its subdifferential is maximally monotone. And if C and F are the Cayley operators of maximally monotone operators, then we're guaranteed that they have the right fixed points and that their composition is non-expansive. That's kind of, in a sentence, the flow of what we've seen so far. And applying it to f and g, the Douglas-Ratchford algorithm applied to this convex optimization problem amounts to x k plus 1 is equal to the prox with respect to f of yk, and yk plus 1 is equal to yk plus the prox of g of 2 xk plus 1 minus yk minus xk plus 1. So by itself, seeing this might be unintuitive, but seeing the entire development of how this is really just the averaging of the composition of the Cayley operators, how the Cayley operators are themselves created by, sometimes they're called a reflection of the resolvent, and the resolvent is just the prox. It's the backward operator that corresponds to the prox. Then perhaps this puts it in a context where this seems like principled and makes sense as to where we got this, or how we came up with this iteration. So this is one of the basic forms that you'll see in for Douglas Ratchford. We derived a few others in the previous lecture in this series, and in particular, one of the formats that we saw using some change of variables is this is equivalent to, and this is primarily the one that we'll be using in this lecture. UK plus 1 is equal to prox g of xk plus wk. Xk plus 1 is equal to prox f of uk plus 1 minus wk. Again, this is just from the previous lecture. I'm writing it here so we can see it again, and it's what we'll be using. And wk plus 1 is equal to wk plus xk plus 1 minus uk plus 1. The benefit of this format, these are just simple algebraic manipulations to get from one to the other. But this format is really putting it as close as possible to the kind of framework that we've seen it again and again for dual gradient ascent, for proximal point algorithm, and proximal gradient in the dual as well, where basically we were updating our variables using the separable operators for dual gradient ascent in particular, and then for proximal gradient. And notice this is what we're doing. So UK is updated using only the prox of G. XK is updated using only the prox of F. And then WK is just updated using a simple addition and those previous two. So this is the spirit of everything here. We're trying to build a more general theory about how we can take advantage of special structure. So again, at the risk of repeating things that we've heard many times before, dual gradient ascent, what that accomplishes is it just splits the forward operator of gradient and allows us to decouple coupled problems. This was the motivation. So we started with our canonical problem, minimize f of x plus g of ax, but then we saw that under the conditions that f and g are strongly convex, then dual gradient ascent just becomes solving a Lagrangian in f that is unconstrained and uncoupled with g, and separately solving a Lagrangian with g without having to worry about f, and then combining them in a simple update rule, similar in spirit to what we've written here. And proximal gradient was the same thing. What changes is what assumptions do we need to make things work. So this is the general framework. It's not that one algorithm is always going to be better than the other. We're trying to understand, now that we're stepping outside the black box model, based on assumptions that we have about the problem, when can we exploit them in a principled algorithm? So whereas with dual ascent, you benefit if the primal functions are strongly convex, therefore you get smoothness in the dual, so a gradient ascent makes sense. You can do acceleration and so on. In this case, we see what the primitive computational steps are, and it's prox of G and prox of F. So Douglas Ratchford makes sense when the individual operators are themselves relatively easy to evaluate. And that's the whole idea of operator splitting. We're dividing and conquering and dividing into pieces that are themselves easy by assumption. In this case, where the assumption is that prox G and prox F are easy to evaluate. So this is the idea. Let me just finally write that down. We need prox G and prox f evaluations. That's of course through the case throughout. Similarly, it's just like saying that the Cayley operators are easy to evaluate. And then the final note that we made in the previous lecture is that we can also clearly, in terms of finding the solution, the argument of f of x plus g of x is the same as the argument of any positive scaling of f of x plus g of x, lambda f of x plus lambda g of x. And it, if you go through this algorithm, you'll see that it's in fact not invariant to scaling, unlike other algorithms that we've seen. And so if we scale, all of these prox functions just become the scaled prox function. And as we've seen, the scaling a prox function, including in the proximal point algorithm, is really equivalent to something like a nonlinear step size, essentially. If we, so applying to minimize lambda f of x plus lambda g of x, where lambda is positive, we get the same update, except we have prox lambda g and prox lambda f in the above. So let's move to see a few examples of Douglas Ratchford. Now, a lot of these, I'm just going to outline the problem, and I'll really leave it as an exercise for you to write down, to go back and try to write down exactly what the updates are. So I think that will be a good exercise to solidify what Douglas Ratchford is, and really what these forward and backward operators are. Forward operator, again, being gradient step, backward operator being the resolvent, or as we've seen, related to the prox. So this is a problem of sparse inverse covariance selection. The idea is that you're getting samples from a Gaussian graphical model. If you've looked at Gaussian graphical models, you know that the graphical model is given by the sparsity pattern of the inverse covariance matrix. But if you just look at the sample covariance and you take its inverse, it's going to be dense just because of statistical noise, and therefore we want to extract a sparse matrix there. But it's sparsity in the inverse. So the data are given in the covariance matrix, and we want sparsity in the inverse covariance. And you may want to do something better than just take the inverse and threshold, since taking the inverse could create problems. So I won't say more about the origin of this problem, but that's basically where it comes from. So let's just write it down. Sparse and inverse covariance selection. One way to solve this is to solve the minimization problem. Min dot product between matrices C and X. C is given, and X is what we're solving for. So this is a minimization over X. I want to make sure that X is positive semi-definite. Rather than adding it as a constraint, I'll put it in the objective function. Covariance matrices and their inverses are, of course, symmetric and positive semi-definite. And I want to encourage sparsity, and I'll do that with an L1 penalty. Gamma is a regularization coefficient, and this is basically the L1 norm on a matrix. Just absolute sum of absolute values on the individual unique entries. So I'm going to apply Douglas Ratchford. I'm going to let this first term be F, the second term be G. The exercise that I would like for you to do, really for all of these, and for additional examples that you may find, is to look back at UK plus 1, we'll just write what was on the previous page. UK plus 1 is equal to prox lambda g of xk plus wk. Xk plus 1 is equal to prox lambda f, for f and g as above, uk plus 1 minus wk, and wk plus 1 is equal to wk plus xk plus 1 minus uk plus 1. But let's just look through it and see why this makes sense. The easiest is prox lambda g. We know that this is easy. We've seen this before in connection to ISTA and FISTA when we were talking about proximal gradient, and why it makes sense to break off the L1 norm in order to get back a faster convergence for something like squared norm, squared loss plus L1 norm. And basically, so we know that prox, so the exercise is to write these updates explicitly. When I say explicitly, as in, the step before you implement it. So just so you know exactly what it is. But prox lambda g, we know this is soft thresholding. Soft thresholding. And in particular, it's easy to compute. What about prox f? So perhaps this takes a little bit more thought. So let me just get you started a little bit here in terms of thinking about this. So prox f, I need to compute the argmin of f of x plus an L2 term. L2, because we're in a matrix, is really going to be the Frobenius norm squared. So I need to, there's a few challenges here. So to help you along with this, let's say one hint is that the derivative of log det x looks a lot like the derivative of log x. Instead of 1 over x, it's x to the minus 1. Actually, there's a transpose there, but for us the matrices are symmetric, so it's just x inverse. And then you're going to be then you've got a linear algebra problem, really. What you're just writing this down. If I write that x hat is equal to prox lambda f of z, what you're going to find using this this expression for the derivative of log det is this is that 0 is an element of c minus x hat inverse. That's the gradient of log det. C is the gradient of c transpose x, and then I have to deal with the L2 term, or the Frobenius norm. Well, that's easy. That's my usual 1 over lambda times x hat minus z. And now the question is, how do I solve this? It turns out that this is takes some computational expense. You basically need to solve an eigenvalue decomposition on c minus lambda z. So let me just take one more step, and then I'll leave it to you. Rearranging, it's not much help. This is the easy step. X hat, I get x hat minus lambda x hat inverse is equal to z minus lambda c. And so now my hint to you is the following. It's that these are all symmetric matrices. So we all have, so everything inside is a symmetric matrix. Z and C, those are the data matrices. Or what's given. C is the data matrix. Z is just my previous, is what I'm applying prox to. So it's given. X is what I'm trying to find. So note that on the right-hand side I have a symmetric matrix. And therefore, let me write it in a different color since this is my hint here. So this is equal to the sum of mu I vi transpose. And on the left-hand side, note that x and x inverse, though they have different eigenvalues, their eigenvalues are related in a very specific way, and they have the same eigenvector decomposition. X hat and x hat inverse have the same eigenvectors. So I'll stop here with a hint and let you finish it. The main thing, I mean, you can solve this little linear algebra problem here, but that's just a step. I really want you to be able to write down exactly what the Douglas-Ratchford updates are.